Hello, my name is Madison Koppelman, and I'm here to talk to you today about the synergistic effects of all trans retinoic acid, ATRA, on triple-negative breast cancer cells. I'm under the advisement of Dr. Sanku Malik at North Dakota State University in the Department of Pharmaceutical Sciences. To begin, triple-negative breast cancer is the deadliest breast malignancy and comprises 10 to 15% of cases. Solid tumors develop early and harbor drug-resistant cancer stem cells. All transretinoic acid, ATRA, induces differentiation of cancer stem cells in a variety of solid tumors. Herein, we demonstrate the synergistic effect of doxorubicin and ATRA on cytotoxicity of triple-negative breast cancer cells in a monolayer and describe the methods of ATRA quantifications by high-performance liquid chromatography, also referred to as HPLC. A little introduction: solid tumors are a unique tissue type with many distinct characteristics, including a hypoxic and acidic tumor core. The breast cancer solid tumors also display a heterogeneous cell population that includes cancer stem cells. These cancer stem cells do not respond to first-line chemotherapy, and in order to increase therapeutic efficacy, cancer stem cells need to be eliminated to increase tumor homogeneity. ATRA has been previously identified to induce differentiation of cancer stem cells. So the objective of my project is to increase triple-negative breast cancer cell homogeneity in hypoxia to increase the efficacy of first-line chemotherapeutic drugs on triple-negative breast cancer cells in a monolayer. To begin, we started with creating an ATRA standard curve on our HPLC. I have listed the instrument parameters we used, as well as the methods. First, we created 10 known concentrations of ATRA, measured the area under the curve for their absorbance, and then generated the standard curve. This is the standard curve we generated. On the right, you can see the respective concentrations and their areas, as well as the equation for our line and our R-squared value of 0.99. We can later use this graph to measure the efficiency of our drug-loaded polymeric nanoparticles. Next, we looked at an ATRA doxorubicin synergy experiment. We cultured MDA-MB231 cells in complete DMEM media, seeded 5,000 cells per well in a 96 well plate, incubated for 24 hours in normoxia as well as in hypoxia, dosed the plates with varying concentrations of ATRA and doxorubicin, incubated for an additional 48 hours, then analyzed the cytotoxicity with an Alamar Blue assay, calculated the cell viability, and analyzed that viability data using a cost-benefit software. Using that software, we generated this first graph. Along the top, you'll see the respective dosing range that we used for ATRA in nanomolar, as well as doxorubicin on the left. At about 1,500 nanomolar ATRA and 1,000 nanomolar doxorubicin, you can see a high synergistic effect in hypoxia. However, in normoxia, where we had an N of 5, it can be argued that there is little to no synergistic effect between doxorubicin and ATRA. So, for future directions, we can do future exploration of dosing ranges for both ATRA and doxorubicin to really key in and identify the optimal dosing ratio. ATRA will also be encapsulated in polymeric nanoparticles to increase the efficacy and overall drug delivery to solid triple-negative breast cancer tumors. My work is being funded in part by the Department of Pharmaceutical Sciences at NDSU, as well as the EPSCoR DREU student grant. My references are listed below. Thank you.